Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Let's get started. Today's lecture is about making the computer fast when it comes to using dynamic libraries. So this week we're going to be talking about dynamic linking, and it gets the same job done as static linking does, but it works very differently. When we talk about static linking again, to review, what we're doing there is we're making one big happy executable. We're taking our individual code segments from our main.c, as well as our standard libraries. And we're bringing them all together into one executable. We get one a.out over here on the other side, and that is the final result there. This gives us an executable that is going to run, in this case, basically on any version of Linux. You throw it at that version of Linux, and if it was compiled with the right kernel options, it's just going to work, which is really, really useful. Now, on to dynamic linking, wildly different. What we're going to do here is rather than put everything into one file together, we're going to keep these files separate. We're going to have access to them at build time, but we're not going to bring them in. So at build time, we've got our main, we've got our library, and the compiler is going to do that same relocation step that we had earlier on, where we're going to have these relocation entries, but we're going to leave those relocation entries as just relocation entries that a special program called the dynamic linker is going to do for us when we actually start the program. So what we end up with after building is a main with a few pointers that will go into a specific library. So we got our a.out here, and they're going to go into that library when they get used. So that fix happens at invocation time, which is pretty crazy, right? We're doing all this work on the front end to just get that final bit done right there at the end. And this is one of many different concepts that kind of blows my mind. It's kind of like, why are we even trying to do that? It definitely sounds harder. It definitely sounds slower. And we're ending up in a situation where this couldn't possibly be better than just static linking. We saw static linking, it works well, it gets the job done. What's the big deal? So this is a great time for us to step back and figure out what we're doing as systems designers. And this is a little bit of a 2-for-1 for you all in the audience. You're going to see both how the system is built that you're building on top of as a programmer that makes programs that runs on operating systems. You can actually see how those parts work. And if you know how they work, you have a good idea of how to make your individual program a lot better and a lot faster. The other part here is really, it's like deep. It's kind of like the other important part here is a little bit more subtle, but it's also just as important, if not more so. We're learning how a bunch of people, decades ago decided, hey, I have a system and I need to make it run faster. I need to make it run faster, and I need to keep it correct, but I'm willing to add complexity to the system based on what I know about my workloads, based upon what I know about how fast my computer is and what different parts are fast, what different parts are slow. I'm going to add this complexity to the system, which will make it work out much better in the end based on that workload. So this is a great example of what we're trying to learn here. And even if you're not going to be building your own dynamic linker sometime in your next job, you're still going to be able to take these approaches of looking at how an entire system works and saying, okay, here is how I'm going to make this faster. Even if you're not going to introduce a new algorithm that's n log n instead of n squared log n, whatever have you, it's going to be better. So our job is to make things that are both good and fast. They're not going to be cheap because you're going to get paid well for it. One side note that I like to give in class that I'll randomly end up saying at some random point in class, but today because we're recording, I'm going to say it specifically right here, is that if you are building a system for your boss, for your job, for the business that you run or work for, whatever have you, there's two ways that you can optimize that system. One is that you can make it work correctly, and two is that you can make it fast. What I like to say is that whether you can make it work correctly or not is a matter of whether you have a job or not. Like if you don't make the system work correctly, then you're going to get fired, right? You're not going to be able to even get the job in the first place. But whether you can make it faster or not is whether you get a raise, whether you get a promotion, things along those lines. Being able to do both of these things is important, but let's be clear, making sure that things work correctly is priority number one. So if we bring this back out from just talking about individuals that are working in jobs to talking about designing systems, systems fundamentally need to be correct. If it doesn't work correctly, nobody's going to use it. But at the same time, there's lots of different systems that people can choose to use, and they're going to choose which one they want to use eventually based on which one's faster, right? Maybe you've been using the same thing for a really long time, but there's some newer, faster thing out there. It's like, well, I'd have to retool all of my code, or I'd have to recompile things, or I'd have to change the way I do things. But eventually, people are going to start using that faster one. And knowing how to build these things faster, knowing how to say, I'm willing to put more complexity into my code in order to make it faster is an important thing to do. So the other thing that I wanted to say in this slide is that we're showing you how to make things that are good. We're showing you how to make things that are fast. And the not cheap part is that you're paying for this education. So the education doesn't come cheap, but at the same time, once you learn this, you won't have to sell that education that you have, that ability that you have for cheap. I definitely want to see you all getting those awesome jobs. Just let me know how I can help. So let's bring this back to dynamic linking. What's so good about it? I'm not going to talk about how it happens. We're going to cover that in the next video. But right now I'm going to talk about the whys of why we're going to add all of this complexity. What is that benefit that we're seeking by changing the game on how we include libraries? So the first benefit that you're getting out of this is that you can interchangeably update the programs as well as update the libraries without having to ship the entire update to that individual computer. So for example, let's say I've got program 1 and program 2 and program 3, and each of them uses library 1, library 2, and library 3. Like, they all use all three of these libraries. In a static linked world, if any of those libraries had a bug in it or got a new version that was faster, we would have to update program 1, program 2, and program 3, all of them, because they rely on that one individual library, right? That's not the most efficient thing in the world. And every time you ship a new update to an individual library, you've got to ship updates for every single one of those programs. If you had a really popular library like the C standard library that got updated, you'd basically have to update every single program on your entire install, and that is just not worth doing, right? However, in dynamic linking, if we leave these libraries on the disk and we don't change anything about their definitions, like the type signatures of the function calls, then all we need to update in the case that library 1 gets updated is just library 1. That's going to be much, much more efficient when we run our program. Another benefit, and this is going to look a little bit forward in class to some topics that we haven't covered yet, is that when we keep our libraries separate from our running programs, we only need to keep one copy of that library in memory, no matter how many different programs are using it. So TLDR, when we have an individual chunk of a file that's stored read-only in memory, we can keep it there and share it among as many different processes as we want. So if, again, we've got program 1, 2, and 3, all using libraries 1, 2, and 3, by a little bit of math, we'd have to have 3 copies of library 1, 3 copies of library 2, and 3 copies of library 3 if we were running one instance of each of those in the static linking world. In the dynamic linking world, we would have to have 1 copy of lib1, have 1 copy of lib2, and have 1 copy of lib3. We're going to rely on the operating system's ability to share memory between processes to actually share this 1 copy of library 1, and 1 copy of library 2, and 1 copy of library 3 into those 3 individual programs, which will make things a lot more efficient when it comes to our use of memory. Now, that efficiency isn't just going to bring our amount of free memory down, allow us to run extra programs, allow us to use more memory in our programs, which it does. The really awesome, amazing part about this is that by using less memory, we actually end up making our program run faster. And it's not just going to be, oh, it takes less time to load because there's less bytes to load. One really important concept about copying these things into memory is that we have this cache hierarchy that we learned about in 261. There's a very, very tiny amount of very expensive RAM that goes super, super fast. Then we have an L2 cache, an L3 cache, an L4 cache, etc., that are relatively small, but very, very fast stores for memory. And if we can keep things in those levels of the cache, our entire program runs faster. So if we have fewer bytes of our program especially fewer bytes that get used over and over and over again very often, we're going to have to pull things into cache less often. We're going to have to make those really expensive calls out to main memory less often, and that will make our program much faster, which is really awesome if we think about it. And if there's one thing that I want you to take away here, besides all these other important parts, is that using less memory, even if we control for how long it takes to load it, will actually make our program faster by making the resident size that goes into the cache smaller. That will in turn make the overall execution time of our program shorter, which is good. Sounds pretty awesome, right? Well, when we start using dynamic linking, there's a lot of extra complexity here. Remember, when we used static linking, we looked things up, we pulled them in the linker, and we had this executable ready to go. It's just going to jump to the correct place every single time it wants to use a function like printf. So what if you've got 17,000 different copies of printf in memory? It works the way that you want it to, and is correct. With dynamic linking, there's a lot of extra work that has to happen, both at build time, as well as at load time, as well as when you invoke that individual function, but it is going to end up being faster. This additional complexity is what we're going to learn about here. And remember that there's two things we're learning here. One, we're learning how that dynamic linking works so that when our programs break, we know what happened, we know how to fix it. The other thing I want you to take away from this is that when you see a problem like make this faster, you need to take the same idea of, well, let's add a little bit of complexity, make things work in a different way, but knowing how our system works, knowing what it takes its time to do, will give us the inspiration to figure out, aha, here's a new, completely different, but altogether faster way to do this. And then you'll get that promotion. And then your system will run faster. And then everything will be happy. And then, hooray,